This is Chapter 6, Lecture on Gasoline. So for every barrel of crude oil, 87% of it is used for the purposes of transportation and heating. So a barrel of crude oil is about 42 gallons. And so 50%, half of that barrel, is used for transportation purposes, meaning that half of that barrel of crude oil is used to make things like gasoline, jet fuel, diesel fuel, and so on and so forth. So to meet the large demand for gasoline, the higher boiling point fractions, which are larger in molar mass, meaning they have a larger number of carbon atoms, they are sent through a process called cracking. The cracking takes place down here for fractions in the crude oil that have between 15 and 18 carbons and between 16 and 20 carbons. And so this little cracker device that's attached to the distillation column operates under high temperatures, because as you go from the bottom of the distillation tower up to towards the top is where you have the lower temperatures. And toward the bottom of the tower is where the temperatures are at their highest. And so therefore, going through the cracker device will crack or break up those large molar mass fractions that have between 15 and 18 or between 16 and 20 carbons into smaller hydrocarbons. And therefore, the refinery is able to make even more gasoline and jet fuel and diesel fuel down here from these higher molar mass fractions. So what is cracking? Cracking is just breaking up a large number of carbons containing hydrocarbon into two smaller molar mass pieces. And it's done so by high temperature, which is called thermal cracking. And also there's catalytic cracking, in which a catalyst is used to get the temperature at the optimal level in order for cracking to take place. So for example, if we have a hydrocarbon that is a 16 carbon hydrocarbon, so the formula is C16H34. And then under high heat, that alkane gets broken up into two smaller pieces. One piece has 11 carbons, the other piece has 5 carbons. And so this 5 carbon piece is pentane. How do I know it's pentane? How do I know it's an alkane and not an alkene or alkyne? An alkene would be having one double bond. Alkyne means it's a hydrocarbon that has at least one triple bond. Well, I know it's an alkane with all single bonds because of the formula C5H12. It's of the form CnH2n plus 2, with N being equal to 5. That makes the formula C5H12. Now C11H22 is an alkene. There's a one double bond in the formula of this compound. This formula is of the form CnH2n, making it an alkene. And so catalytic reforming using a catalyst is going to involve the rearrangement of atoms within a molecule. So reforming takes place in the upper part of the distillation column. And so hydrocarbons with between 5 and 12 carbons will be in this upper region of the distillation tower. And what the reformer is going to do is converts linear alkanes into branched alkanes. And those are called isomers. So an alkane can have a linear version of itself and what we call also a branched version of itself. For example, octane has 8 carbons, so it falls within this 5 to 12 carbon fraction of hydrocarbons. And so linear octane is called N-octane. So that's the linear version of octane. So in the reformer, the linear form of octane is converted to the branched form of octane called isooctane. And so isooctane is a much better fuel for your car engine because it allows your car engine to run more efficiently by preventing engine knock. So that's what the reformer does. It rearranges the atoms of the hydrocarbons that are between 5 and 8 carbons. And those molecules between 5 and 8, between 5 and 12 carbons, they start out in linear fashion. And the reformer converts them from linear to branched. And the linear and branch version of a hydrocarbon they're called isomers of each other. So why is the branched version of the alkane different from the linear version of the alkane? Well, the linear alkanes are going to have stronger London dispersion forces and therefore higher boiling points. The branched isomers are going to therefore have weaker London dispersion forces and lower boiling points. And so isooctane is one of the more popular branched hydrocarbons between 5 and 12 carbons. And it's used as a gasoline additive to prevent that engine from knocking and helping the engine run more efficiently. So if we compare these first 4 alkanes, methane, ethane, propane, and butane, you can see the difference in molar mass and boiling point temperature. Methane is CH4, ethane is C2H6, propane is C3H8, and butane is C4H10. So you can see as the molar mass increases, so does the boiling point. And so now if we look at the other part of this figure, we see 2 isomers of pentane. The first isomer is the linear version shown here on the right. And it's called N-pentane. And then the branched isomer is over here on the left. It's called neopentane. The proper systematic name for it is 2,2-dimethylpropane. The common name for it is neopentane. You can see that they have the same molar mass because they've got the same structural formulas. This one is C5H12. This one is also C5H12. So they've got the same molar mass because they've got the same formula. But note the difference in their boiling points. The branched isomer has a lower boiling point than the linear isomer. And the reason for this is that the linear isomer has greater surface area than the branched isomer. So having a lower surface area gives it a lower boiling point. So that's how the branched isomer is different from the linear isomer. So therefore, if you increase the surface area of an isomer, being that the two isomers are going to have the same molar mass, so when you're looking at two isomers with the same molar mass is not going to explain the difference in boiling point because they have the same molar mass if they are isomers of each other. So the only thing that can explain the difference in the boiling points is the difference in surface area. So if you increase the surface area, you increase the boiling point. So here are our two isomers of octane. You got your linear octane called N-octane. And then you've got your branched isomer, isooctane. The branched isomers are always going to be more compact. And so therefore less surface area. And so your linear isomer is always going to have greater surface area. And so we talked about how isooctane, when added to gasoline, reduces engine knock and helps the engine run more efficiently. And so the gasoline octane ratings was developed to indicate the gasoline's quality related to knocking. The higher the octane rating, the less knocking the engine experiences. And so note that isooctane has the 100 octane number rating, whereas N-octane, the linear isomer, has a very low octane rating number, -20. And then other additives that have been popular to put in gasoline to improve the octane number are things like methanol. And of course, most of us right now probably have gasoline in our car that has a certain percentage of ethanol in it as well as isooctane. A compound that used to be used is called MTBE. Even though it gave great octane numbers, it's very, very toxic. And once it was discovered how toxic it was, its use was discontinued. So in the following question, we have an isomer of butane. And so each of the dark black spheres are carbons. And then each of the gray spheres are hydrogens. And so this is butane with the formula C4H10. And so we want to draw the formula for this isomer. It's going to be CH3, CH2, and then we've got another CH2, and then connected to that carbon on that last CH2 is a CH3. And so in drawing the structural formula with our CH3, CH2, then we've got another CH2 on the end, and then connected to that carbon is another carbon, which is a CH3 carbon. So there's the structural formula for this isomer. And notice that it is branched. And so it's compact. The other isomer is going to be the linear version of butane. It's not going to be branched. So it's going to have the same formula, C4H10, just like the branched isomer is C4H10. So you're going to have your 4 carbons connected. You're going to have 3 hydrogens attached to the carbons on the end, and then 2 hydrogens connected to the carbons in the center. So this is the linear isomer of butane. And so the branched isomer is going to have the lower boiling point, because it has less surface area. The linear isomer of butane is going to have the higher boiling point because it has the higher surface area. Next question, and that's a typo there, that should be ethanol. We've got the structures of ethane and ethanol, as well as ethene, the alkene with a double bond. So is ethane an isomer of ethanol? Well, no, it's not. Ethane has the formula C2H6. Ethanol has the formula C2H6O. Ethanol has an oxygen in its formula. Ethane does not. That is why they are not isomers. Isomers have to have the same formula. Next question. We have a reaction that's representing the process of cracking a 16 carbon alkane is the formula CnH2n plus 2. Sixteen carbons, so N is 16. And so 16 times 2 is 32 plus 2 is 34. So you've got your 34 hydrogens. And then it gets cracked under high temperatures to two different pieces, one piece with 5 carbons, the other with 11 carbons. So we looked at this previously. This is pentane, an alkane, and this one is an alkene with the formula CnH2n, with N being 11. And so which bonds are broken and which bonds are formed in this reaction? Well, when we take a look at bonds broken, we've got 16 carbons in our alkane that we're going to crack or break up. So let's draw our 16 carbons. And so the carbons on the end are going to have 3 hydrogens attached. And the ones in the middle are going to have 2. And so I'm not going to write in all of those H's for the conservation of time, but at the end of each of those lines, there's a hydrogen understood to be there. Okay. And so these first carbons, that's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So we get a product that has 5 carbons and then another product that has 11 carbons. So that means after the 5th carbon, this bond had to be broken in order to get a C5H12 product. So this bond getting broken we'll be left with the first piece, but note that this is C5H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But we need 12 hydrogens. So what's going to happen is, in order to form the double bond in the other piece, so the other piece, the 11 carbon piece, will be these. And so this is where the two piece is split. And so this piece has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 hydrogens. But you only need 22 hydrogens. So the extra hydrogen one of these hydrogens, therefore, is going to be transferred here to form a new bond. So this bond here has to be broken so that that hydrogen moves over here. And that is what's going to create a double bond. And therefore we have our alkene. So now let's analyze bonds broken and bonds formed. So we have this first one that I've drawn in purple, that carbon-carbon bond there. And also in the second piece, that carbon-carbon single bond had to be broken in order to form the carbon-carbon double bond. So we've got two single CC bonds broken. And you have this CH bond broken here. And that hydrogen transferred over to the 5-carbon piece. Now let's talk about the bonds formed. We know we formed one C double bond C bond in our 11-carbon piece. And then we also formed a new CH bond over here in our 5-carbon piece. So let's find the bond energies a CH bond is 416 kilojoules per mole. And then let's see, that was a CH. So it's 1 times 416. And then a CC bond is 356. So 2 times 356. Add those together. You get 1,128 kilojoules. And then the bonds formed. Again, a CH bond is 416. A CC double bond is 598. And then add those together. You get 1,014. And bonds formed, remember, is exothermic. So we got to put a negative sign. And so therefore, answering part B and A at the same time. So we talked about which bonds are broken and which bonds are formed. And now let's get the energy change. The delta H is going to be 1128 plus a negative 1014. And that is going to give us a positive 114. And that brings us to the end of our pre-class lecture video on gasoline, as well as the cracking process and the reforming process.